So we are taking a look at page 12 notes, and we're starting our unit on matter and energy. So the first thing that I want you to know is that the universe represents everything, and everything in the universe in science is classified either as matter, which is made up of particles, and each individual particle contributes mass, which we tend to measure or quantify in grams. And every individual particle occupies space, which also refers to volume. So every particle has some volume, and we tend to quantify or measure it in liter. Now, matter, we will subclassify matter to compare and contrast it. And so we can compare and contrast the matter based on its state, or what we might refer to as its phase. So I'm going to write the word phase here. Another word for the state of matter, phase of matter. And our three forms of matter in everyday life that we look at is if the sample is a solid, a liquid, or in the gas state. The second way that we can compare and classify matter gets a little bit more into the chemistry is the composition. And what I mean by composition are what type of atoms are present. So what type of atoms make up the particles, so the type of atoms, and then not only the type of atoms, but their structure. How do those atoms link or bond together? The other major component to the universe besides matter is what we refer to as energy. And energy represents our ability to do work. Now, in our everyday lives, we recognize 8 different forms of energy. And usually how we name that form of energy is depending on how we access it or use it. So most of these you should be familiar with. So the first one I'm going to list is heat, which is also referred to as thermal. Another major one is light. And you've probably heard this referred to as radiant energy or solar energy, but I'm going to put another word here because I'm going to need more space. Is also light is known as the electromagnetic spectrum. So I'm going to write electromagnetic. We will come across that term quite a bit in chemistry class. Moving on, think about what you use to get ready. So electricity is a major form of energy. Sound is another form. We don't always think about sound as a form of energy, but it is. A scary form of energy would be nuclear. We have mechanical energy. We have magnetic energy. And probably one of the most important forms of energy, but you might not realize that it is also considered a form of energy, is chemical energy. And like chemical energy, examples of chemical energy would be things like the food you eat, because that supplies batteries, or gasoline for your vehicle. Those would be all examples of accessing chemical energy. Now, No matter what form of energy we are referring to or thinking about, we quantify it or measure it in the unit of joule. And the symbol for joule is a capital J. Every form of energy can be described with both of these characteristics. So we have kinetic energy that is kinetic in nature versus energy that is potential in nature. So if we describe our energy as kinetic, that means that it is in motion, or the energy is being used. Versus potential energy. If a form of energy is being described as being potential, then that means that the energy is simply stored. It's not in motion, it's not being used, it's being stored for a future use. Now, as we work through chemistry all year, we always have to keep in mind the law of conservation. So the law of conservation states that everything in the universe is conserved during all changes, whether they're physical, chemical, or nuclear. So for us, we will look at each of these individually during the school year, but this is something to get memorized because you're probably going to be asked a question multiple times. What is conserved? Well, everything's conserved. So the three major areas, no surprise here, is that mass, as in the particles of matter, is conserved. The amount of energy is conserved. And something else that we'll talk about later in the school year is charge. So these are three things that we track during changes that occur, and they are all conserved: mass, energy, and charge. So specifically, the law of conservation of energy, it simply states that energy cannot be created or destroyed during a chemical reaction. So we can't make more energy out of nothing, and nor can we make the energy disappear out of the universe. So the number of joules before the change is absolutely equal to the number of joules after the change. The differences in the energy is what happens to the energy during the change. It's not created, it's not destroyed, but energy, it can be transferred between samples. So think about transfer of location. So in this sample here, we have an ice cube, and it looks like this ice cube is melting, right? So what does an ice cube need in order to melt? Well, somewhere from its surroundings, there is a transfer of heat, maybe from the air or whatever surface the ice cube is sitting on. So the air transfers heat to the ice cube, and we know that there's heat transferring to the ice cube because we can observe it melting, changing from a solid to a liquid. In this other picture, looks like we have a hot cup of coffee or hot chocolate. So in this case, we know that the transfer is opposite, where the beverage starts off extra hot. It feels really, really warm to our touch, but as you allow it to sit there, it starts to cool down. And because the sample, the beverage, is releasing or giving heat off, and that heat leaves the hot beverage, and it leaves and goes to the air. You can feel it on the surface of the cup or the counter that it is sitting on. Now, one major thing that you probably already know is that heat always flows from the warmer sample to the cooler sample. And this transfer of heat will always flow from the warmer to the cooler sample until they reach the same or similar temperatures. That's always the natural direction of heat flow. Moving on to page 13 in the notes. So here we go. The other thing that can happen to energy besides it being transferred from one material to another material is that energy can actually change forms. So if you think about it, we utilize electrical energy all the time, but we start off with electrical energy and we change it into more useful forms. So great example here is a battery. So any type of battery represents chemical energy. Now the battery by itself isn't very useful. You put it into a piece of equipment like a flashlight and you hit the on switch for the flashlight and the chemical energy starts to transform into electrical energy, energy traveling down metal contacts and wires. But it's not the electrical energy we're interested in when we're using a flashlight. The electrical energy reaches the bulb, and then you have a filament of some type, and it starts to give off radiant or light energy. So the purpose of using a flashlight is for that radiant energy. But to get that radiant energy from a flashlight, we start off with chemical energy in the battery. It changes to the